Today we're talking colors, so stay strapped in because we're about to talk about titration. Lab 11 was titration of an antacid. An antacid being like breaking that down. Ant means to antagonize, which is just the abbreviation, and an acid, of course, being an acid. Everyone knows what it is. So our antacid is an antagonist to an acid. If you're wondering what this antacid is, we used these like Tums. In the case that we used in lab was these equate like sugar calcium pills that help to break down acid as it's coming up through the esophagus. So this titration, what we tried to do was we tried to find the moles of our HCl that react with the base inside of the antacid so that we could reverse that into finding out how much calcium carbonate was in our specific tablet and then turning that into how much calcium we had inside of that tablet. The biggest thing with this one was that we should have found a solution that whatever is proposed on the bottle is not actually what is inside of the bottle. So first, when working with titrations, we're going to have our burette and we're going to have whatever flask is below it. That burette is going to have very minute details, and hold on, my laundry's done. Sorry about that. Okay, so our burette is going to have very, very precise values. What we're focusing more on is bringing our water values to a hundredth value. Typically, whenever we're working with our graduated cylinders, we can see that it goes to the different tenths, but because a burette is so precise, we can actually go to our hundredths value, and that's incredibly important when we're working with our solutions because we want to be as precise as possible. When it comes to titration, it could be within a drop of solution that you can get colors to change. It's very, very precise. So let's talk about it a little bit. Titration as a concept is a practice of putting two acids and bases together inside of a dyed solution to find the perfect ratio of both. As we've been doing throughout the semester, we've been mixing HCl and NaOH together. We know that if we were to combine 1 equal part of HCl with 1 equal part of NaOH, that both of them should combine and create a perfect water and salt solution. This is how we can prove that. So using our burette, we were able to fill it up with a sodium hydroxide solution. That solution being whatever we measured, we did our part 1, which was trying to figure out the true concentration of our NaOH solution, and then going into part 2 with the part 3, with trying to figure out how much of that we can put into our solution to figure out how much of the antacid is in our tablet. So starting with that part 1, part 2 thing where we're trying to solve this whole thing out, it's a pretty simple solution of getting a certain molarity and trying to make a 0.1 molar solution. What we would do there was we would put that in our burette, of course, and then having a KHP solution dissolved into an Erlenmeyer flask and filling that with a few drops of phenolphthalein, not phenolphthalein. I'm sure you could say it that way. I'll probably make fun of you for it, but it's phenolphthalein. As we're doing this as we're doing this experiment, we are opening the burette slowly to let this solution drip through. What's very important with this is that you need to continue to stir it, otherwise you'll just have this pool of changed dye. This stirring helps mix up all the different parts in the solution, and it helps it make homogeneous. If you've learned about it in lecture, homogeneous means to be completely indistinguishable by the human eye. Chocolate chip cookies are not homogeneous. They're heterogeneous. I don't know what the word is. They're not homogeneous. You can see the different parts. You can see the chocolate. You can see the batter. You can see them all split up. Whereas for these solutions, as we're stirring them, we're trying to keep them homogenized. We're trying to make them into a one complete solution. However, as we're doing this, we're watching for color change. Phenolphthalein, while it is acidic, is clear. It shouldn't have any color. As we're adding the NaOH, because it is completely dissociated in water, being that it's a strong base, that OH, or the hydroxide molecules, will start to react with phenolphthalein and create a pinkish color. what we're looking for in the end is a very subtle pink color in our Erlenmeyer flask. Um, and it may be the case that you get it there, you stir it, and it's clear. That means you are incredibly close. You're just going to keep adding this until you see that, like, within one drop, it goes from clear to very light pink. That's how we know we have reached a neutral sort of area. We have equal parts OH and equal parts H, because OH and H, they'll try and attract each other. It should turn into water. However, if we've gone to very light pink, we know that we are on the precipice of jumping into the base area. Now, you would have seen that I put a few more drops of dye in there to make the color stronger, because it's a bit harder for me to see colors when I have two pairs of glasses on. So while I was doing this, you could see that there was a much more distinct lighter pink color, and then when I added that extra, it was almost like a purplish color, like a pink. Um, that being said, that one drop difference is what makes titration so delicate a procedure that we can start to prove our other concepts in chemistry, that being stoichiometry, empirical formulas, molecular formulas, and piecing all those together into this nice bow of we know that these are true because we can practice this in a very closed system. However, if you're listening to someone argue saying, like, oh, well, if you leave it for long enough, it'll start to dissociate, the pink color will go away. Yes, because, and this, I cannot stress this enough, CO2 is acidic. And the longer you let it sit, because we have a natural amount of CO2 in the atmosphere, it may start to diffuse into our solution or get inside of our Erlenmeyer flask and start to get rid of that pink color. So if you see that happen, I tried to demonstrate it in lab. It didn't go very well. But as you're seeing this and it's starting to dissociate and it's the pink color starting to go away, you know that over time there is an acidic part of the atmosphere that's getting into that solution, making it less basic. So keep that in mind. Moving on to part 3, where we actually get into the back titration part, and this is where our antacid comes in. I'm going to show you this graph that you should have been given in your books, but I'm going to go ahead and explain it into some greater detail just because it's more important for you to know. So I'm going to sit over here because I got extra space. This is our sort of diagram of what we're going to be working with. Our antacid, first, we're taking a small amount of it, a small mass, and we are putting it into a solution. We're going to crush that up, make sure that it's completely homogenized, and then what we're going to do is we're going to start adding HCl to it, and that's going to create an acidic solution with both our antacid and our HCl. And keep in mind, none of our base or acid leaves the system. It stays in there like forever until you get rid of it. So when we add our antacid, we have a certain mass, it's stuck in there. That is our unknown. We don't know how much calcium carbonate is in there, the base that we're tracking. And when we add this HCl, that is one known value that we have. I'm sure you could probably figure out a way to do all this if you knew what the ratio of calcium carbonate in this whole solution was, but for practical purposes, and because we don't always get 100% yield, we're going to do a back titration to track the actual amount that is in the solution. Keeping in mind that if you're going to do just these two, you're going based off the numbers on the bottle. You're taking the word of the company over your own scientific principles. So when we do a back titration, we're going to add all this HCl, we're going to have an acidic solution. This time we're not using phenolphthalein, we're using bromoscol green. I think I said that right. Bromoscol green? Bromcrysol, not bromoscrol, or whatever I said. Bromcrysol green at neutral is green. That's why we call it bromcrysol green. When it is all the way in this acidic side, what we're going to see is a yellow color. As we start to add our NaOH, we're going to start going back to our neutral, which is our green, and then jump into our basic side, which is our blue. Still, what we're trying to do is we're trying to track the volume that we're getting rid of, and at least from the first part, which I'm not going to spoil it, but from that, what we were tracking was the true molarity of NaOH. You can go back through in that lab. I can give you some values to work with if you weren't there for it, so that you can sort of figure out how to do that. And then, of course, you can always ask questions, and then I'll help you through it. So once we have two known values, and I'll go ahead and write down that this is a known value, we now can come to the conclusion that whatever we have up here and whatever we have down here is going to give us whatever's over here. That's a very important part of the equation, because if we're trying to find our antacid and we just have this, we don't have this. We just have all this. So now that we've added this NaOH, we can bring it back to neutral. We can find this part. So sort of how this is going to work is we're going to be working with moles for this because our different molar ratios are empirical formulas, and sort of trying to use stoichiometry to solve through how to sort of break this down. We're going to be focusing more on the moles and the ratios that we're using in these equations. So let's go ahead and have our base A, which is our antacid. We're going to, that's our variable. And then if we have a acid, H, which is going to be our HCl, we're going to subtract that concentration of base N, which is our NaOH. Whatever we have left over is going to be our concentration in moles of our Ba. However, it doesn't stop there. When working through this equation, calcium carbonate reacts with HCl in such a way that you need 2 HCl for every 1 calcium carbonate. So once you find the moles of this base, you need to divide it by 2. So whatever this value is now going to be the true moles of calcium carbonate. From there, of course, you're going to want to find the molar mass of calcium carbonate, which for this lab was 100. You're going to, you're going to multiply that through to find the mass, and then whatever mass that is, you're going to take a percentage of that mass to find the calcium contained within that molecule. Since calcium has a mass of around 40, 40 of 100 is just 40%. Once you find that mass of the calcium carbonate, multiply it by 0.4, and then you get your mass of calcium. The Tums that we were working with in lab, the Equate brand, which I think is your Walmart brand, it advertised that there was 400 milligrams of calcium in each of those tablets. Of course, because of human error or some other experimental factors that we weren't keeping track of, we should have been close to 400, but we may not have been exactly at 400. There may have also been a bit of lying on the end of the companies that are making this because they don't have the very specific, like minute details that they're sticking to. They're throwing all this in a vat and expecting it to work. So what we were doing for this case was we were tracking how much of the base that we were actually getting compared to how much we were actually using here. Now I know that none of you are going to leave this lab and say, oh, I'm going to go do a titration somewhere else. Well, very important thing that you may want to know is when it comes to your Tylenols, your ibuprofens, when it comes to like actual chemicals that you may be working with, this may be a beneficial thing to know. So I used to do EMT training in high school because it was really the last class I could take as part of a medical pathway, either that or CNA, and I chose EMT. There is a specific amount of Tylenol that you can take per day, and there's a specific amount of ibuprofen that you can take per day. I believe for ibuprofen it is 600 milligrams, and for Tylenol it is around 4,000. I'm going to double check that real quick. I'll be right back. Okay, so I was pretty close. 4,000 milligrams of Tylenol or acetaminophen is your cap. You don't want to go any higher than that, otherwise you start to run into complications. It has been advised to me, though, that you shouldn't cross the 3,000 boundary. Of course, working in this titration lab, there may be a specific value that they may be putting more acetaminophen in the Tylenol than what they expected, so it's really safe to stay around the 3,000 just in case you're taking more. Drugs that do contain acetaminophen are Tylenol, Excedrin, paracetamol, Panadol, and Sudafed. It's very important that if you're taking Sudafed for allergies, is it Sudafed? I think it's Sudafed, or Tylenol at the same time to keep track of the amount of acetaminophen that you are taking. And then, of course, for ibuprofen, you have your Advil, Motrin, Midol, and Genpro. When it comes to ibuprofen it says that 800 to 1200 milligrams per day is safe. You should probably get a doctor's recommendation to go higher than that. Biggest thing with those, as like a life lesson thing, and this will be the only one that I have for this review, make sure to eat before taking those because they can cause damage to your stomach lining. But if you're eating something at the same time, you don't have to worry about that. So anyway, titrations, that's the long short of it. It's a very delicate lab to do, but in the end, it's a practice that we have. It's a really good example of how to do chemistry and how precise it is when we're working with solutions. Now for Lab 12, I will not be going over it in a video, like I've said before. We will be doing this in class, and if you have any questions over it, feel free to message me. This one is over molecular properties, and we are working with lycopodium, which is incredibly flammable. That's just like a cool thing for you to know. Yeah. All right, guys. So have fun. They sell gloves. I guess that's a fun fact for you to know. I use them for painting because I don't want to get oils all over the paint. Water paints and oily skin don't mix. So that's of course, you probably already figured that out by now. Anyway, have a good one.